Hello, hello, sir.
Hello,
Hello, sir. Good morning,
good morning.
sir. I sent a mail yesterday regarding the quiz about the.
That okay. If 100 people in different dates, that will be difficult. I discussed in last class, right? Did
Yes,
you
sir.
be there in lab in class last class?
Yes, sir. Means
Yes.
mm,
Then why did you even tell me?
actually
I
it
think you are
wasn't
not there.
means at that time I particularly might have missed.
I don't know because I don't check these ones. Only 30, 40 people comes in class about 140. Okay, we discussed a lot of in the beginning. Okay, so I think now we cannot do that. Okay, because we discussed a lot which time previously Friday, Sunday I don't want to schedule. Then Diwali people will go home. Okay, so yeah, what is your problem? I mean,
So actually at that time I think I might be traveling. I might not reached home by that time.
I think you skip that. Where is your home?
Means my home is in Odisha. I'm traveling.
Traveling. Look, it will be difficult for traveling purpose. Okay, this is IIT.
Okay.
So, okay, so my traveling and those kind of excuses is unacceptable in IIT. It's not like in high school or college. You understand? So, I mean, otherwise, other people will be there. They will also give excuse. No, this kind. It happens when we discussed. Friday, then also some. Actually, we wanted to schedule at 6. Then someone also told that they have some online something with the University of Waterloo or something. Yeah, where? So I schedule happen hour before. So now it is not possible. So you should skip. You go next day. Okay. That's why I am telling that you attend the class. Okay. There are a lot of informations not only for scheduling things. As it will be difficult to manage. There are a lot of people, 140 student. So everyone tells like that, then this is not possible. Okay. So you go home next day, Sunday.
Yes, thank you.
There are only 23 people. Where are the other people? 23 out of 140. So this is the effect of online class, right? Okay, let's start. Do you have any questions? Questions from the last class? Any doubt? Hello, can you listen? Can you hear me?
Yes, sir.
Yes.
Yeah, okay. So no questions. Okay, so let's start. Okay. Yeah, so whatever I will be teaching until today, so I will finish the isotope effect. I am teaching slowly. That's okay. So that will be the syllabus of the quiz. Okay. Yesterday I sent the email. I hope you all of you received. So it will be on Saturday, right? On 30th October. What time? I forgot. 5:30. What time is your quiz? 5:30.
Yes, sir.
Yes.
5:30 to 6:30. Yeah. Someone also asked me to reschedule. So if you can prepone half an hour. So that I did. Okay. Okay. So now time is fixed. And I will send an email. Okay, so to whom you will send, and yeah, send some other information about the quiz. So it will be 10 marks, 10 marks, and we can do together. Okay, and I will give the proper instructions. So for there will be part 1 and part 2. So you need to write it down separately in separate papers. Okay, and you need to scan and send it to different email ID. Okay, yeah, but I will write in details probably day after tomorrow on Friday. Okay, so this is the last slide I discussed last time, right? So primary kinetic isotope effect, you can see that the bromination of toluene or even chlorination of toluene, or last one is the oxidation of chromate. Those are high kh by kd, and if it is more than 1.5 or 1.5 at least, that indicates that this is the this is the kh by kd is because of the primary kinetic isotope effect. CH or CD bond is broken in the red determining step. But I highlighted this red color box, right? This is the nitration of benzene. This is the industrial procedure to afford nitrobenzene. Nitrobenzene has a lot of applications. Okay, one of the primary application of nitrobenzene is reduction of nitrobenzene to aniline, and aniline has a lot of industrial applications to make dye, a lot of fine chemicals. Okay, even in pharmacy, aniline is used. Okay, even paracetamol is starting material is aniline. Okay. All right. And benzene, from where we get benzene in industry? From petroleum oil. Okay, it's benzene. So that is a this is the industrial procedure. So kh by kd. So if you want to study what is the mechanism, then kh by kd is basically one that indicates that CH or CD bond is not broken in the red determining step. So what might be the mechanism? This is a very common mechanism. You may also know from your, I don't know, high school, you know that or not? You may. It is a very simplest mechanism. Okay, this is basically the electrophilic substitution reaction. So HNO2 is nitric acid and sulfuric acid. It gives the NO2 plus electrophile. Then electrophilic substitution. Oh, I should. Yeah, so the first step is that the reactions with nitric acid and H2SO4, it gives the electrophile NO2 plus, and then electrophilic substitutions occurs with benzene, right? So this process, it involves in the transition state 1 to give the carbocation, and then deprotonation take place. Okay, sorry, deprotonation take place to gives the nitrobenzene. This is a common pathway of electrophilic aromatic substitution. All right, so there are two transition state 1 and transition state 2. Okay, so you can see the first one is that one transition state, that is the attack of the benzene to the electrophile take place, right? And second one is the CH bond is being cleaved here. CH bond is being cleaved. So if you determine the rate law first, okay. Anyway, the first is kh by kd for particularly for this case. But regardless, whatever you will, whenever you will determine the kh or kd, you need to find the rate law first. So rate law is the first step. Okay. So let's skip the red law for now. So kh by kd indicates that the ch or cd bond is not broken in the rate determining step. So you can see that ch or cd bond is broken in the second step in transition state 2. So transition state 2 or second step is not rate determining step, right? It's not. So obviously the first step is the rate determining step. So kh by kd helps a lot to determine what is the rate determining step in a multi-step reaction. Okay, is it clear? So you can see here in transition state 1 that CH or CD bond is not being broken in the first step. That is also being supported by kinetic isotope effect KH by KD. It is equal to 1. Is it clear? Clear? So first step is the rate determining step that is supported by KH by KD. Good. So so definitely you can also predict, okay, that I may ask you that what kind of experiment you will do to establish this mechanism. Then first is obviously the rate law. So rate law will tell that definitely it will be the first order with respect to benzene, and okay, first order with respect to benzene, and it will be zero order. Okay, it will be difficult to measure, but still if you have NO2 plus, okay, suppose, then definitely it will also be the first order with respect to NO2 plus, right? And yeah, and what will be the activation parameters? You can see this will be the positive or negative. Del S of activation, what will be the sign?
Negative.
Negative, because two molecules are coming close to each other and forming a complex in the transition state 1. So this is here you should expect that entropy of activation will be changes of entropy of activation from starting material to the transition state is negative, means decreasing. Okay, and this kind of rate determining step is also supported by the value of kh by kd. So far we have learned the 3 experimental techniques to find the rate determining step. All right, I told a lot of things, right? So but those I'm repeating again and again and again. All right, so again I'm coming back to this slide. The case number 1 that I discussed last time, last class, that this is the elimination reactions, right? If you replace the middle CH2 to CD2, then KH by KD value is 6.7. So that indicates that 1 degree means primary kinetic isotope effect. Okay, and we also discuss about the transition states, right? E2 versus E1. So that indicates that CH or CD bond is broken in the transition state, and this KH by KD value is quite high. So that indicates that this O hydrogen carbon, this bond angle is close to 180 degree. It is almost linear transition state. That's why KH by KD is very high, right? So it is KH by KD value is supporting the E2 mechanism, the possible transition state in the rate determining step, and it is ruling out, okay, the possibility of E1 mechanism, that is the formation of carbocation, because here CH or CD bond is not being broken. All right. But what about the second case? The second case, the blue case 2 in the blue color, you can see that here now this is a tertiary carbon, right? This is a tertiary carbon in water. It is also giving alkene. Here is the same thing, only you are changing the CH2 to CO2 and it is giving the alkene. Here you can see KH by KD is 1.4. That indicates that this is a secondary kinetic isotope effect. That means whatever the rate determining step is there, in the rate determining step, CH or CD, CH, this CH or CD, because we are replacing here, okay, here CH, you are replacing this CH, so this CH bond, whatever I circled here, this CH or CD bond is not broken in the rate determining step, right? If I tell or speak faster, let me know. So what does it mean? So, and what is the origin? Next I'm going to tell. So far from the value you can tell that 1.4 kg by kd is an example of secondary kinetic isotope effect. What have I told, right? So CH or CD bond of that particular position is not being broken in the rate determining step. It will be broken, right? At least you can see here that one of the CH or CD bond is broken, right? Here you can see in the beginning there was a D, 1D, there in the beginning it was the 2H, 2D, but at the product there is only one CH or CD. So definitely CH or CD bond is broken during the reaction, but whether this CH or CD bond is broken in the rate determining step or not, that KH by KD will tell you. Okay, so the secondary so the secondary isotope effect is telling that that particular CH or CD bond is not broken in the rate determining step. Okay, so what is the origin of secondary kinetic isotope effect? Secondary kinetic isotope effect, definitely, as I told you, that how the kinetic isotope effect, what is the origin of kinetic isotope effect? Forget about the secondary, primary or inverse. The kinetic isotope effect is originated, we told that, right? That is because of the different difference, okay, of 0 point energy of CH and CD in the ground state versus excited state or transition state, right? So whatever the difference of 0 point energy, we told you previously, again we will discuss in the next, okay, the whatever the 0 point energy, the difference of CH or CD, if it is the same ground state versus excited state or transition state, then KH by KD will be 1, right? So barrier is the same for CH or CD bond on the bond energy difference. But if it is different in ground state versus excited state or transition state, then there will be an effect, right? So how much effect? That governs that is the primary, secondary or inverse if it is a reverse way. Okay, so normally the secondary kinetic isotope effect, the value is greater than 1 but less than 1.5, small amount, typically involves a change in bond hybridizations from ground state to the excited state, or maybe there is will be involvement of the bonds in hyperconjugation. So you can see the bond hybridizations or hyperconjugations that may affect little bit, that can perturb the little bit of the energy of the vibrational energy or vibrational levels of CH or CD bond. Okay, and because of this effect, because of the hybridization or hyperconjugations, if the energy levels of CH or CD bond affect differently in ground state versus excited state, then definitely you will see a primary, definitely you will see a kinetic isotope effect. But since CH or CD is not being broken, so whatever the effect you will see because of this, that will be small amount. So that will give you a small value change, and those are the origin of secondary kinetic isotope effect. It can be normal secondary or maybe inverse. All right. So as I told, that secondary kinetic isotope effect. So this kind of things, it can give rise of this normal secondary kinetic isotope effect or inverse, but value will be small. If it is inverse, it will be like 0.8, 0.7, okay, something like this, and this is in between 1.1, 1.5 if it is normal. All right. So now let me tell you in a very simple and pictorial way to understand that how the hybridizations or hyperconjugations, okay, that affect the vibrational energies of CH and CD differently in the ground state and excited state. So let's talk about, suppose here you can see in the slide, okay, it is very clean slide. I have taken from the book of Dennis Dougherty, okay, that I also, that the reference books that I also gave you in the flyer in the beginning, and the library has multiple copies. Okay, that book is very nice. Okay, if you can read, if you want to explore more, but in class definitely I will highlight, right, and tell you briefly, but in a pictorial way so that you can understand easily. So let's talk about the carbon center, that which is sp3 hybridized, suppose here, okay, and sp2 hybridized carbon atom. Okay, so I hope no sp3 and sp2, what is that, right? So this is the sp3 hybridized carbon atom, and this is the sp2. When you will get sp2, this is the alkene, right? And sp3, you know from your high school when it is alkyne, right? So let's talk about sp3 and sp2. Suppose sp23 is the ground state, okay? Suppose it is an SN1 reaction, stebutyl bromide, you remember. So ground state is sp3, but in the rate determining step, carbocation is formed, right? So sp3 is being converted to sp2, right? In SN1 type of reaction, you remember. So now look at in sp3, when it is sp3, CH or CD bond is not being broken. This is a secondary kinetic isotope effect. So there are a lot of other vibrations. One is the in plane vibrations, another is out of plane vibrations. Those are called bending vibration. Okay. So CH bond, if it is CH, oh, if it is like this way and this way, then this is called stretching vibrations. Okay. If it is this way, but H is the, okay, if it is like this way, it is vibrating like you are twisting the spring, then those are called bending vibrations. Okay. So now you can see in sp3, this is kind of symmetric, like a methane molecule. Okay. So this is kind of symmetric, right? So here suppose we have a methyl group. Okay. Methyl groups, and you have a CH. Now we are talking about the CH bending vibrations. Okay, so it can bend on the left hand side, whatever I have shown the arrows on right hand side. So if it is bent right hand side or left hand side, or maybe in front of the screen, okay, in front of the screen, out of the plane. Suppose in plane you are looking about your desktop or computer or maybe mobile, right? So let's assume that plane is your screen, okay, or you are, if you are drawing, then blackboard is the plane. Okay, so in plane means it is vibrating on the left hand side or right hand side along the screen. Okay, okay, there is another one vibrations, this is called out of plane vibrations. Out of plane you may consider is that CH or CD bond is vibrating on the back side of your screen or front side of the screen. Is it clear? If it is no, let me know. Tell me. Do you understand my point? In plane and out of plane? Yes or no? Hello?
Yes, sir.
Yes,
Okay.
sir.
All right. So out of plane means it is vibrating above the screen. Above means towards you, towards your nose, right? If you are sitting, or back side of the screen. All right. So you look at, okay, in experimentally, suppose this is the in normally in CH out of plane vibrations, bending vibrations, it comes 350 and also the bending is 350. Why? Because the environment in 3D OA, okay, is 3D, okay, all metals are in a equally distributed. So if it is in plane vibrations, out plane vibrations, it will be the same. Sterically, environment of the CH bond is same. It doesn't matter in which way it bends. Am I correct? If it is left way, right way, maybe on the diagonal way, doesn't matter on which way it vibrates. Relatively, the environment is same because these three metals are in three dimensionally, it is equally distributed. Okay, in a 3D way. So the out of plane, that is in plane or out of plane, energy will be almost same. But what about sp2? sp2 is different. This is a, this sp3, this is a the carbon is tetrahedral, right? But in sp2 this is the planar, correct? So you can see the in plane, when it is in plane, whatever the arrow is here in plane, it is more sterically hindered, because if you plane then it will be CH2, on the this side there will be CH3. Okay, so it will take more energy for in plane vibrations, and normally from IR it's this vibration energy comes around 1350. It is almost same. But the difference comes for out of plane vibrations. You can look at when it is out of plane vibrations, then if the back side or front side there is no other atom. This is the free. Am I correct? It is free.
Yes, sir.
Yeah, this atom and this side is in plane. But if this CH bond is vibrating above the plane, or back side of your screen, there is no atom. So there is no steric on out of plane. So the bending vibrations that is out of plane for sp2 hybrids, it will take the same displacement. You remember this plot, okay? So the same displacement, okay? This is the displacement, right? So you are stretching or bending. So displacement will take lesser energy. Am I correct? Because there is no steric in out of plane. There is no other atom in the out of plane. So whatever the bending vibrations you take, it will take less energy. That's why your value is less, is 1 by lambda centimeter inverse. So it is lower in energy, right? It is lower in energy. So I hope from this
Yes, sir.
3D picture, from this 3D picture, from this pictorial representation, whatever I'm trying to teach you, it is obvious that why for sp2 cases out of plane vibrations takes less energy compared to sp3. I hope it is clear. If it is not, I will repeat again. Tell me, is it clear or not? Any questions?
Sir, please repeat it again.
Okay, I will repeat it again. So, for sp3, as I told you, that CH bond, two type of so let's consider the simplest way. Two kind of vibrations are there. One is in plane, another one is out of plane. Whatever the screen you have here, right? The screen, whatever your screen, I'm not talking about my screen, your screen, your mobile laptops. Think about that. Your screen is the plane, the actual, the in plane, out of plane. So that is the one reference is there, right? One is the basis. So that screen is the plane. Okay. Yeah. PLAN is correct, right? PLANE. Is that spelling is correct? I think so. Yeah. So this is the screen. Screen is the plane. So CH bond can vibrate left hand side, right hand side along your screen on the plane of your screen. Those are called in plane. Or if CH or CD, if it is vibrate upward, means towards, okay, the vertical or 90-degree or vertical way of your screen or backside of your screen, those are called out of plane. Is it correct? Is it correct or not? You understand my reference?
Yes, sir.
Okay. Sometimes if I draw this unnecessary lines comes in the left hand side. I'm drawing in mouse, but anyway. So hope it is fine. Now for sp3, this is symmetric 3D. This is a tetrahedral structure. So CH bond is vibrating left clockwise, anti-clockwise, not clockwise. It is vibrating in the left hand side or right hand side, in the plane or out of plane, doesn't matter. It will find the similar steric environment because all these three atoms are equally distributed. You can see this one is the back side, this is front, this is plane. It's a tetrahedral, right? So the CH bond, it doesn't matter on which directions it moves, outer plane or it out or in plane, the same amount of displacement is vibrations. I'm talking about displacement, right? Vibrations. It will take the same energy in plane or out of plane. Is it clear? Or no?
Yes, sir.
Yes. Because whenever it is finding back way or front way, it will have the similar steric environment. Okay, so the energy of vibrations will be same for CH or CD. You can see the values 1350, 1350. All right. What about the sp2? In sp2, there will be a difference of energy of vibration in plane and out of plane. How? In plane, it is similar to the in plane of the sp3. Okay, so if it is bending this way or this way, okay, suppose the atoms are there, okay, so the energy will be the similar to sp3, but for bending will be totally different. For the bending, sorry, not bend, all are both are bending, but bending for out of plane vibrations for sp2. So you can see the CH or CD, it will vibrate above the screen or below the screen, but okay, so above the plane or below the plane, but on above or below there is no other atom because these two atoms are in plane. This is sp2 hybridized. This is not sp3, sp2. So this is a planar structure. So if CH bond, when it vibrates out of plane, bending, then it will take significantly lesser energy compared to in plane. Because in plane there are sterics, it cannot vibrate much. Because if it is vibrate more this side, there will be a steric of this. If it is vibrate more on this side, then there will be a steric of this. But out of plane is free. It can vibrate more easily using the same energy, right? So out of plane for sp3 will take much lesser energy. 800 centimeter inverse is 1 by lambda, right? This frequency. So it has less frequency. Is it correct or I will repeat again? If it is not, let me know.
Yes, sir, it is fine.
Is now I will repeat again. Don't think that okay, you are wasting others' time. Okay, if it is even further doubt, we can discuss at the end or maybe next class. Let's say every beginning of the class. Okay, I hope you will not complain that okay, the instructor or professor is not giving us opportunity to ask questions. Okay, right? So I am giving a lot of opportunity to ask questions, even though it is taking my teaching time, but it's okay. I no need to teach more. I think if I teach less, that's fine as long as you can understand. Okay, and remember after the even after the course is over, CML 103 is over. All right. So you can see here from whenever from the ground state to excited state, if there is any change of hybridizations, starting material is sp3, but transition state or redetermining step, the hybridization is changing. Okay, then the energy level of CH or CD will change because of the difference between the this and this energy. Okay, so this is common for CH or CD. So okay, this is the value of CH, but you want to determine the secondary kinetic isotope, means you need to replace with D. So look, which has more vibrations? Which has more vibrations? CH or CD?
So H.
CH always has more vibrations, right? It vibrates more, right? It always vibrates more because the vibrational frequency is inversely proportional to the root over square root of mu. So whatever the changes of out of plane vibrations, okay, the effect will be more on CH than CD because CD is inert. For example, suppose there are two guys, one is a thin guy, okay, and one is a fat guy, okay. So fat guy doesn't move much because he is heavy, right? So thin guy will vibrate more, right, because he has more energy, he is thin, he can travel fast. So suppose both are same, okay, suppose both of them, I'm just giving another representations. Suppose there is a lockdown, not suppose, we had a lockdown, right? So fat guy and thin guy both are sitting in a or enclosed in a room, and suddenly release them after 1 year, okay. So you will see that both are released, both were enclosed in a or locked in a room, but when you release them, okay, both will be excited to vibrate more, okay, they will explore outside, but definitely the thin guy will be more excited than fat guy. Fat guy will tell, I understand, after 1 year of lockdown I want to explore more or want to travel here and there, but it's because of this fatty nature, he cannot move much. I'm telling just like in a practical human beings, okay. So thin guy will travel or do trekking or whatever more than fat guy. So similar to like this you may consider, okay. So whatever the changes of out of plane vibrations from sp3 to sp2, okay, it is coming from mathematics, but I'm just telling in a pictorial way. The effect of vibrations or the difference, you can see the difference, okay, the 350 to 800, this difference, okay, this is the 0 point energy you can consider, okay. The difference of ground state and excited for CH will be more compared to CD because the effect of these out of plane vibrations will be more on CH than CD because CD is relatively inert. Is it okay? Is it clear? Okay. So whenever you are replacing CH or CD, there will be a changes of vibrational energy, suppose 0 point energy in ground state and excited state, okay. So in secondary kinetic isotope effect, it is easy to remember the way I'm teaching. So if you see that the ground state is sp3 hybridized, so we can tell this is the tight vibrations. As I told here in the before, you can see sp3 hybridized, it doesn't matter it is the in plane vibrations or out of pipe vibrations, you may tell this is tighter because if it is vibrate it will have a steric here, if it is out of plane it also have a steric here, so it is quite tight, that's why it needs higher energy, okay. So it will be easy to remember, okay. I'm telling this term, the tight vibrations, the vibration is quite tight, it is not easy. But when it is sp2, in plane is tight, but out of plane is loose, okay. So you may tell if it is the sp2 hybridized, it is the loose vibrations compared to sp3, okay. So whenever a transition state is happening, ground state to transition state, that sp3 hybridized starting material is converting to sp2 hybridized in the redetermining step, then we may also tell tighter vibrations to loose vibrations. Okay, it's clear. So how it will affect? If it is tighter, it will be thinner. Tighter is tight, right? Tight means if you want to vibrate of the same displacement, it needs more energy, so it will more stiffer, right? And if it is loose, you can see this is flat. It's more flat, right? It is more flat. Is it correct? Have you seen this flat? And I also told that when it will be flat, means loose vibrations, then the effect of CH will be more. So CH will vibrate more easily, means it will take lesser energy compared to CD. Okay. So in short, if it's loose vibrations, then the energy difference between the CH and CD will be lesser in the excited state compared to ground state. If it is tight to loose, it's very simple. Okay. So you can see here, if the ground state to excited state, if it is tight to loose vibrations, then kh by kd will be greater than 1 or is less than 1? It will be greater than 1. And you will see normal secondary kinetic isotope. Okay, not inverse. Okay, we will come with examples. It will be very interesting. You can predict also what you can see. The opposite situations, you may also see that ground state is have loose vibrations and redetermining state has tighter vibrations. One of the example is sp2 type of reactions. We discussed more before also many times, right, in each and every stage. So here you can see this is sp3 hybridized. But what about the excited state or redetermining state? This carbon center is 5 coordinated. So this CH, when it is vibrates, it will take more energy because it is more spherical. The carbon center is more spherically hindered. Its P character increased. It is like a trigonal bipyramid, right? sp3d type of things. If it is d orbital like metal. Okay. So here carbon center is 5 coordinated. It is 5 coordinated, so this CH or CD will have more tighter vibrations, so it will be tight vibrations. As I told, if you go loose to tight, then the CH or CD difference will be more in excited state than ground state. Okay, so on those cases, what you will see? You will see inverse kinetic isotope effect, and this is true. Kh by Kd is always less than 1 for SN2 type of reaction. I will come up with example. So you can predict if this is the mechanism, what type of Kh by Kd you will see, or opposite way. If you don't know the mechanism, Kh by Kd will tell that in the what will be the possible geometry of the transition state or redetermining state is what will be the, so that will also gives a hint that what will be the change of hybridizations from the ground state to excited state. All right, now let's go to the example. I have 5 minutes. Okay, look here, let's go the first one, because first one is primary kinetic isotope. I'm not talking about primary, let's talk about the secondary. This is the addition reactions of ketone. Whatever the H star, that means you are replacing H with D. That's why it is H star. Okay. You can see this is the addition of Cn minus. This is the hydrocyanation reactions with ketone. All right. Okay. Okay. Just give me 1 second. I think I didn't take any break, right? Just 1 second. Okay, can you hear me? Hello? Hello?
Yes, sir.
Oh, okay, okay. All right, so this is the addition of CN minus with ketone. You can see obviously the ground state of ketone. This is the substrate. You are talking measuring the Kh by Kd. This ketone, this is the sp2, and what about the rate determining step? You can say it is obvious the product is forming sp3. So this is the loose to tight. So what you will see, what you should expect loose to tight. Loose, tight. It will be inverse. C Kh by Kd is 0.73. Okay. What about here? This equation. Look, how Kh by Kd is helpful. Thus, the number, this is called number 1, number 2. Number 2 is very interesting. It can also tell you what will be the mechanism Kh by Kd. Exam may come like this way. So this is the hydrolysis of benzyl chloride, papaver methyl benzyl chloride. H star is the CH by CD. In ethanol, it is giving alcohol. So Cl is replacing with alcohol. So there are two type of mechanism. One is it may be SN1 or SN2, right? So water may attack here, and it can go SN2 type of mechanism, or it can for carbocation. Okay, that is SN1 type of mechanism. So I told you that SN1 and SN2, it will have different effect of Kh by Kd. So if it is SN sp2 to sp3 means sp3 or reverse, so sp3 to sp3 something more like SN1 type of SN2 type of mechanism, then this will be the loose to tight. So loose to tight for SN2. So what will be the Kh by Kd? It will be
less than 1.
Less than 1. We discussed last time. And it is, if it is the, so this is the SN2, and if it is the SN1 type of reaction, then this will be
So tight to loose.
Tight to loose.
Greater than 1.
Greater than 1. What is the value of Kh by Kd? Experimental value 1.3. So what does it mean? What is the mechanism?
SN1.
SN1, not SN2. Yeah, this is SN1. We may confuse that which one will be correct. Okay, first rate law will also tell, also it will be hint. But you can see interestingly Kh by Kd, CH or CD bond is not being broken. But so it is a secondary effect, but you can see from tight to loose or loose to tight, from the value you can also tell that this experiment, this reaction is going via SN1 type of pathway. And why? Because whatever the carbocation will form, this is conjugated. Am I correct? This is conjugated. That's why carbocation formation is being facile. It's stabilized by plus R effect of the phenyl rings. So this is not a SN2 type of reactions. This is a SN1 type of reactions. All right. What about here? The third number. You can see, okay, this is rearrangement reactions. So this is going something like here. This is the mechanism. Rearrangement. If you hit, so this is the sp3 hybridized, tight at the end, loose. So what you should see? Kh by Kd. You can predict it will be less than 1 or greater than 1. This will be greater than 1, but less than 1.3. See the value 1.37 experimental value. Okay. Is it clear?
Yes, sir.
Is
Yes,
it
sir.
interesting? Okay, I will stop here. I think I have only couple of slides. Maybe I will take another half class on the tomorrow. Then I will finish. Okay. As long as you can understand, that is fine. Okay. Any questions? You read. If you have any questions, I will discuss tomorrow first. Okay. And I will take probably another half class maximum to teach you about the heavy atom isotope effect. Okay, then I will finish. Okay. So, any questions? Let me stop recording. Yeah. Any questions? If it's not,